welcome back for our second video in the section 9.3 integral test and P series. And in this video, we're going to look at a result of the integral test by looking at a very specific type of series, what we call a P series. And so a P series is a series of the form 1 over n to the P. So P is some power of n. So the main series 1 over n, and n is raised to some power. So 1 over n squared, 1 over n cubed, 1 over n to the 1/2, 1 over n to the -3. P is some power of n. So we call it a P series, 1 over n to the P. And so what we're going to look at is how the integral test can answer a P series in general. It'll tell me, given P, whether or not this series converges or diverges. So we're going to answer it in general. So we consider a continuous function, f of x, continuous on 1 to infinity, 1 over x to the P, agrees with my series or my sequence terms everywhere. And we're going to look at the case when P is not 1. We'll see why in a second, but P is not 1. So we'll look at every case except this case, and then we'll answer this case separately. So for right now, P is not 1. And so let's look at the integral. The integral from 1 to infinity, 1 over x to the P dx, and the integral test tells me, hey, whatever happens to this integral is what's going to happen to the series. And so remember, we don't like the whole infinite thing here, so we'll replace infinity by t and then take the limit as t goes to infinity. And this is a very simple integral to take, right? 1 over x to the P, let's write it as a negative exponent and use my power rule. So 1 to t x to the negative P, 1 over x to the P or x to the negative P, and use my power rule on it. And I can use my power rule because P is not 1. That's what makes the difference here. So we get x to the negative P plus 1 over negative P plus 1, evaluated from 1 to t. Now, the way that this looks, let's clean this up a little bit. I'm going to write this as 1 minus P and 1 minus P so that the positive term is first. That's just a matter of preference. X to the 1 minus P over 1 minus P. Evaluate from 1 to t. And so we need to evaluate this from 1 to t and then get an answer. So let's go ahead and plug t in. So we get t to the 1 minus P over 1 minus P. So let's just go ahead and factor that out. Minus plugging in 1 for x. 1 to any power is going to give me 1. And so we're just going to get minus 1 over 1 minus P. But both terms are going to have the 1 over minus P out. So I just factored it out front. And then we just need to take the limit as t goes to infinity. And in fact, that 1 over 1 minus P, right, that's a constant. P is just some power of n. So it can even be pulled out of the limit. And really, we need to answer this question. And before you say that this blows up to infinity, or it's t to a power, it's infinity to a power, remember, it depends on what P is. Because in fact, if P is a number bigger than 1, then this number will be a negative exponent. So if P is bigger than 1, like 2 or 3, then 1 minus 2 or 1 minus 2, that's now a negative power of t, and therefore it's actually in the denominator, right? Negative exponents means it's in the denominator now. And when I let the denominator blow up to infinity, that actually converges to 0. And so in this case, or in this situation, we have to think about what's going on with the value of P. If P is bigger than 1, then this value will go in the denominator. Then when I take that limit, it will go to 0 and leave me with this. We'll get 1 over 1 minus P. This will go to 0 times negative 1. So we'll get negative 1 over 1 minus P. Well, that's something finite. That converges. And therefore, the series converges. So if P is bigger than 1, the series converges. P is bigger than 1, this guy's going to go to 0. I'll be left with this number times -1, but that's fine, whatever, it's a finite value. And so it converges. If p is less than 1, let's think, if p is less than 1, like 1/2, 0, -1 even, or -2, then this number is still positive. 1 minus -2 is 3. And it will stay in the numerator. If p is less than 1, this power of t will stay in the numerator, and when you do let it blow up, it will blow up to infinity. So that integral will go to infinity. We go over here to the next side. Infinity minus 1, well, that's still infinity. Infinity over 1 minus p, that's still infinity. And so that means this series, or this integral, diverges. And therefore what we have is that the series itself diverges by the integral test. And so for p series, we get very explicit results. It just depends on the value of p. It turns out that if p is greater than 1, this series converges. If p is less than 1, this series diverges. Now the only question is what happens if p is equal to 1, right? We didn't address that. We said, let's do it for all values where p is not 1. Why do we have to think about that separately? Because, of course, if p is 1, we have an issue, right? We can't use the power rule here. Power rule breaks down. We would get 0 in the denominator if p was 1. And so if p equals 1, we have to think about that case separately. That's going to be the series 1 over n. P is 1, so 1 over n to the 1. And then f of x is 1 over x. We look at the integral from 1 to infinity of 1 over x dx. And of course, we see why now we couldn't have used the power rule, because 1 over x has a very special antiderivative. Let's first fix our infinity issue here. The antiderivative of 1 over x is not a power rule situation. Remember, that's ln of x, ln of the absolute value of x. Evaluate from 1 to t, and then we take the limit as t goes to infinity. So we get the limit as t goes to infinity, ln of the absolute value of t minus ln of 1, but ln of 1 is 0. So we just get ln of t. And if we let t blow up, remember, ln is a very slow but still increasing function. This guy blows up to infinity. And so it turns out in this case, it falls on the divergent side of things. The integral diverges, and therefore this series diverges. So in general, what we could do is now just adjust this by writing this. The one case falls into the divergent side. So p greater than 1, it converges. P less than or equal to 1, this series diverges. And this is a result of the integral test, right? Comparing my function to the integral. And now this very important concept, especially with 1 over x, we need to understand something like 1 over n here, right? The sequence that's being added up. Even though 1 over n gets smaller and goes to 0, right? If we progress through the sequence, 1/2, 1/3, 1/4, 1/5, we're adding up smaller and smaller terms, and those terms are going to 0. However, the sum still blows up to infinity. And so the very important concept that we need to understand with series is going to 0 and getting smaller is a necessary condition for you to converge, but it is not a sufficient condition. This is a perfect example. Just because you go to 0 and just because you get smaller does not necessarily mean that you converge. This series does not. And so we always have to be careful of that. We don't want to make the assumption that, oh, you just need to get smaller and go to 0. That's enough. And in this case, P series kind of illustrate that that's not in general true. And so the P series is another special type of series that we're going to add to our list of special series. It'll go along with telescoping and geometric. And that's because we completely understand them. Now, in this case, we still don't know the sum of the series. We don't have a formula for the partial sums because we use the integral test. And so we're not going to get a sum of the series, but we will get an answer to whether or not it converges or diverges. So this is what we call a P series. And so let's look at a couple examples of p-series before we go. And so I left the integral test here written just to remind ourselves of the test that was used to get this answer. Because at any moment you can answer this via the integral test, but since they are very special types, since they are p-series, then we don't need to worry about the integral test. We can get an answer by just knowing what p is. And so we just need to look at the power here. In the first case, p is 3/2. 3/2 is bigger than 1, larger than 1. And so that means this series converges. This series, 1.001. Very close to diverging, but 1.001 is still bigger than 1. And so this series converges as well. Now you understand that 1 over n is very close to converging. Because now p equals 1, which is less than or equal to 1, and now it's on the other side of things, we are diverging. But you understand that if I add any decimal to 1, 1.00000000001, then this series would converge. So this series diverges, but I mean, so close to converging, very close, but it doesn't make it. This one, well, here you're like, well, what's p? Well, remember that roots are powers, and so we just need to think for a second of the 4th root of n to the 5th is n to the 5/4 power. And so that means p is 5/4. Five-fourths is bigger than 1, and so this series converges. And so if my series falls into the very special class, just like geometric, right, very certain situation, 1 over n to the p, we just need to know what that power is on n, and depending on if that number is bigger or smaller than 1, we can have my answer directly. We don't know the sum of any of these series using this method, but we do have an answer. We do know in these 3 cases that the sum of these terms is finite, and in this case, the sum is infinite. And so what we're going to do next is we're going to look at another test. We're going to ask ourselves, okay, we have the geometric series, we have telescoping series, we have now p-series, and we have the integral test, way to compare our series to an integral. Well, maybe is there another way where I don't necessarily want to do the integral test, or maybe I can't do the integral test, but it's really close or similar to a type of series that I do understand. Maybe it's very close to a p-series or very close to a geometric series. And what exactly do I mean by close? It looks like one of these types of series. I mean, maybe we're dealing with something like this. Well, you could use the integral test on this, and you could do trig sub. You don't have to. It's very close to a p-series. In fact, if that 1 wasn't there, it would be a p-series. The only thing holding me back is the +1. It's not a p-series, so I can't say that it is and use the p-series thing here. I can't use this because it's not a p-series. But it's similar to a p-series. It's close to a p-series. Or maybe something like this. Well, this series is not a geometric series, but if I got rid of those +1s, it would be a geometric series. So it's very close to or similar to a geometric series. Why do I care? Because, well, hey, I know that this p-series converges. And so I'd like to say that, well, my series is close to that, similar to it, so it might converge as well. In the same way, if I get rid of the +1s, it is a convergent geometric series, 2/3 to the n. And those +1s, I don't think they're going to make too much of a difference, so I think it would converge as well. Now, of course, we need to justify that, and that's going to lead us into our next test. And so our next test in the next videos, we're going to look at what we call comparison tests. We're going to compare series to other series that we understand. And that's going to start us off on another adventure. And so next, we'll move into the next section and talk about comparison of series.